So this is an RC circuit. We have a resistor and we have a capacitor and we have switch action. We have a change at time t equals 0. One of the key things with these kinds of problems is to make sure you understand the conditions before the switch action and what's going to happen at steady state, what's going to happen when the transient has died down, and you need to figure out what that transient is. So your driving formula that you're going to use for capacitors is this one. Vc of t equals Vc at infinity, because that's the way it's going to be. That's its steady state, and then the part we're going to put in parentheses here is the part that changes, plus Vc at 0. Now that's where it starts, so you have to get that, minus Vc at infinity, and an E. And you usually say e to the minus t over tau. I usually say minus 1 over tau times t, just so I don't have a fraction in my exponent. It looks better. Okay, so it's same thing. So our goals are, we need to find Vc at infinity, Vc at 0, and tau equals RC. The thing about capacitors is that they cannot change voltage instantaneously. So Vc at 0 has to equal Vc at 0 minus. So if you can find what the voltage is before the switch action, you know what the voltage is at 0, and that's how you go about it. So the first thing you want to do is to draw the circuit, how it looked before the switch. So we're assuming it was connected to terminal 1 for a long time. So if that's the case, then we do have a current going on over here on the right-hand side, but it's not affecting our capacitor. And we're looking for the voltage across the capacitor. We're looking for V of t, so that's what we're looking for. So it had been like this for a long time, which means that the capacitor is acting like an open circuit. So this is time t less than 0. Okay, I'm just drawing it for right now. We'll come back and get information in a minute. I'm just going to go ahead and draw them all. Okay, now when we throw the switch, it looks like this. So that's at time t. And then we also want to see what it looks like at infinity. So at infinity, once again, our capacitor will be like an open circuit. We're going to want to draw one more circuit later on to get our resistance. We'll do that later. I wonder if I did that right. Okay. All right, so let's take a look at this capacitor here on time t less than 0. Notice it's in parallel with the resistor. That means it has to have the same voltage as the resistor. The current is going down the resistor this way. So this is the plus side, this is the minus side. And so I can say the voltage across resistor R1 is I1 times R1, which is 3 kiloohms. And I1 is 4 milliamps, which is 12 volts. So that tells me VC of 0 minus is 12 volts, and so is VC of 0. Okay, now let's find VC at infinity. Notice again we have this is plus, this is minus. Again, it's in parallel with the resistor, and the current is going down the resistor. So that's the plus side and that's the minus side. So that's good. And so again, V will equal IR. So VRL equals VC equals I2 times RL equals 6 milliamps times 6. Is that supposed to be a 2? R2? Yeah. 6 kiloohms. And so that's 36 volts. Okay, so now we have that. The capacitance is given. We have that. That's 0.2 millifarads. Now we just have to get the resistance. So to get the resistance, we take this form of the circuit, and if we have any voltage sources, we short them out. If we have any current sources, we make them open circuits. Okay, so from the point of view of the capacitor, this one is not so bad because there's only one resistor. So that's got to be the resistance that it sees. And so R for this one is just whatever R2 is. So what was R2? 6 kiloohms. Okay, now for an RC circuit, tau equals RC. So tau equals 6 kiloohms times C is 0.2 millifarads. Which is 1.2 seconds. Time constant is in seconds. And then I just like to go ahead and get its reciprocal, because then I have it ready to plug in, is 0.833. So then I plug in to VC at infinity plus VC at 0 minus VC at infinity, e to the minus 1 over tau t. So V of t equals 36 plus 12 minus 36 e to the minus 0.833 t, or 36 minus 24 e to the minus 0.833 t. Okay, now we have an RL circuit, but we want to do the same steps that we did with the RC circuit, finding out what it looks like before 0, and then during the activity and then at infinity. And keep in mind that for an inductor, it is the current that cannot change instantaneously. So we're going to say the circuit had been in a steady state for a long time prior to t equals 0. So that means that our inductor is acting as a short circuit. So we can draw it, this is t less than 0. All right, so when we look at this, we want to figure out what did it look like at t less than 0. Now, I went ahead and made the inductor a short circuit, and I'm going to go ahead and make a couple more changes before I start to analyze it some. Again, I don't like current sources, so a current source and a resistor in parallel, I'm going to change that to a voltage source and a resistor. And the inductor is shorting out R2, so we can ignore R2.
What is that thing beside R1 in the red circuit?
That's R4 that's just kind of sticking up there.
Oh,
Yeah. Sometimes people get upset when I leave it out. It's not doing anything. And so R2 was shorted out, so I took it out. I changed our current source and resistor into a voltage source and a resistor. Let's see, I0 is 5 and R1 is 2, so this becomes 10 volts. The inductor is right here. It's not doing anything, but it's right there. R1 is 2 ohms. Well, actually, it is doing something. It's charged. It has energy in it. And R3 is 3 ohms. So at this point, I have a simple circuit. I've got a couple resistors and a voltage source. I can find the current. V equals IR. 10 volts equals I times 5, or I equals 2 amps. And 2 amps, that is IL of 0. I did not write my equation. What we're looking for is IL of t equals IL at infinity plus IL at 0 minus IL at infinity, e to the minus 1 over tau times t. The difference here is that tau equals L over R, but you'll notice the equation takes the same form. So current through an inductor cannot change instantaneously. So if I was 2 amps at 0 minus, I is 2 amps at 0. So we know IL of 0 equals 2. Now I'm going to draw it as it looks with the switch flipped. So it's going to look like this. So I have it drawn right here. This is at time t equals 0 plus the inductor is going to be acting, and it will be acting as a source during this time period while there is activity going on. But eventually, it's going to discharge because there are no real sources. And so at infinity, it's going to look like this. And since there are no sources, we can say that IL at infinity is going to be 0. Now we have to use this drawing of the circuit to determine our time constant. So we need to find the equivalent resistances. We would short out any voltage sources and make any current sources open circuits, but there are none of those. So first we'll combine R4 and R3 in series. So that's R4 plus R3, and this is R2. And you can see that from the point of view of the inductor, those are definitely in parallel. So R2 was 10, so it's 10 in parallel with R4 is 7, plus R3 is 3. So that's 10 in parallel with 10, which is 5. So R equals 5. So tau equals L over R equals 0.15 over 5, which is 0.03. 1 over tau is 33.33. So I of t equals I at infinity, which was 0, plus I at 0, which is 2, minus 0, e to the minus 1 over tau is 33.33 t, or I of t equals 2e to the minus 33.33